All right, so I want to go over last week's discussion questions. I haven't gotten this done yet, and, and then I'm going to do the video on the presentation, and I'm going to try to get ahead this weekend on this stuff as well as grading and so on. I apologize, I'm a little behind. It's a booming time right now in the computer incident response business. We're taking on work and even turning away work in some cases faster than almost I've ever seen before. It's crazy busy. So yeah, business is good. Business is good is a good thing. It's also a difficult thing. All right, so asset security. Let's talk about these discussion questions from last week, which, like I said, I want to get these grades out for you this weekend. So data remnants. This was the really popular one. Most people answered for this first group. So to talk about the four different approaches, right? We talk about data remnants, which is pretty simple. It's basically data that is still there when you think you're getting rid of the data. And this can be, typically here we're talking about electronic data, but an example could just be, you crumple up a paper and throw it in the trash and you're thinking it's gone, but instead you really need to shred it or pulp the paper or whatever. Pulping being better than shredding because, those are two different approaches for paper. So with electronic media, generally there's these four approaches, right? Overwriting, where basically you say, well, we've got all this data here. Normally when we delete it, the data is still present, but the ability to index into it is all that's really been lost. And so, or as someone referred to as pointers, which is pretty accurate. So the process of overwriting the data just means saying, we're just going to overwrite data on every part of it. They've gone back and forth over the years about the effectiveness of overwriting because there was a lot of theoretical discussion about how the land on the disk where an individual bit is stored is wider than the actual area that is given a specific magnetic field. And so theoretically, even when you overwrite it once, there could be magnetic remnants on either side of that bit, right? Think about like over typing something. Right? If you used a typewriter and you had a bunch of letters and you just over typed them all with the number 1. Well, you'd still be able to read it because the number 1 only covers part of that letter. And they were saying, well, yeah, theoretically you could use a scanning electron microscope, or not a scanning, but a scanning electromagnetic microscope, and kind of read the remaining energy signatures on that land and see, oh, well, right now it's a 1, but it used to be a 0, and it also used to be a 1, and it also used to be a 0, and it also used to be a 1, and there you see the conundrum. This is digital data. It was either a 1 or a 0. So the problem with that concept always was, okay, fine, you can see, hey, this is a 1, but it used to be a 0 at some point. It also used to be a 1 at some point. Unless you can reconstruct the sequence in which it was those things, the data is of no use whatsoever because unless the data, there's only ever been one other thing written to that land, you won't know what specifically it was before relative to the one next to it, next to it, next to it, and you'd have to be able to do this with a whole series of them in order to reconstruct any significant amount of data. Not only that, but the other assertion was that even though it is true, it used to be true that this was a problem, modern media, in order to get things like, I remember the first time in 1994, I remember it specifically because I know where I was at Fort Benning, Georgia, when one of my guys went out and brought home a 1 gigabyte hard drive. You can put a gigabyte of data on this one hard drive. I was like, wow, a gig of data on one hard drive. And it was, full-size hard drive. So in order to get from there to where now the really impressive one I saw the other day is a same-size platter that stores a set of platters that stores 20 terabytes of data. So 20,000 times as much data. The way that's achieved is by shrinking the size of each land. And so that problem of a land being bigger than the area really needed for the magnetic field, the magnetic signature of each individual bit, is really not the case that much anymore. I mean, each land is just big enough for that one bit, and that's it. So the reality of modern hard drives, modern magnetic media, is that overwriting just once basically wipes out all your data. And this has been pretty conclusively proven that other problem is theoretical with most modern magnetic media. Your mileage may vary. It's always safest to do the DoD style thing, which is 7 different writes to each bit. So you're more likely to kind of miss to either side and more thoroughly overwrite each land. Make it really impossible to reconstruct any of the data that used to be there. So that's the thing with overwriting. Degaussing. Degaussing is exposing the whole thing to just one strong enough magnetic field that that everything on there, that all the lands are just impossible to reconstruct whatever could have possibly been there. The thing about degaussing is, really, in order to be effective, it's got to be a strong enough magnetic field. My dad used to have a box that you could buy to erase cassette tapes when I was a kid, and you would take a cassette tape and you would go like pass it back and forth over this box, and it would just erase everything on a magnetic cassette tape. But the thing about a cassette tape is it's just a ribbon of magnetic sensitive material, and that's all. But the hard drive is factory formatted with certain areas that have certain magnetic fields from the factory, and a degausser, in order to really be effective, has to be strong enough to wipe all of that out. So it becomes near impossible or financially impractical to reuse magnetic media that's been degaussed. Usually once it's been degaussed, it's trash. And then, of course, encryption is one method. Encryption is a really, really smart method in a lot of ways. Excuse me, in that everything that's written to that disk, if the key is kept off the disk, then everything that's on the disk, if someone were to take that disk, the disk itself is useless because the key is not present. If proper encryption is used, proper algorithm, following the proper methodologies is used, it's basically impossible to reconstruct what was on that disk without the key, which is not present on that disk. So the fact is you don't have to do anything to deal with data remnants. You can just throw that hard drive away. So the fact that you could potentially recover the data, even though it's gone, is both a good and a bad thing. It's a bad thing in that there's always the possibility someone could get hold of that key and decrypt your data. The good thing is you have that key if you've kept it someplace, and you might be able to recover that data even though it's been deleted. So here's an example. Way back in the early 2000s, or actually, no, this was in the 90s. The Chinese guy, I think it was in the 90s. The Chinese got a hold of a Navy spy plane that had an incident with some of their fighter jets, and they recovered the plane and the crew. Yeah, it was in the 90s. They recovered the plane and the crew, and the government wanted the plane back. We were concerned, they'll get the secrets and so on. So what they put in those planes is and we used to have these in like intelligence offices. You'd have literally on top of every file cabinet a thermite grenade, which is you pull the pin and it doesn't explode. It just burns white hot and burns its way like by gravity down through all the layers of stuff in the filing cabinet. It destroys everything. We would use them in the Army for destroying like guns and piles of enemy guns and stuff. Just pile them up and put a thermite grenade on top, and it would just burn its way through and melt everything. And they would have these things on spy planes. So you would use that to go through all of your hard drives as well, so all of the data that your sensors have gotten won't fall into enemy hands. So, but there's always the problem if you don't want to pull it too soon because you're thinking, it looks like the enemy might capture us, we better destroy the data, but let's wait and make sure, in case we get away, we want to make sure we get this data back to home base. Well, the great thing about encryption, nowadays, those are protected by encryption. The key is stored separate from the drives in a separate electronic device, and you literally throw a switch that's behind like a little protected doorway. You throw that switch and it scrambles the keys. Boom, the keys are all gone. And so now that data is no longer recoverable with anything that's present on the plane. But if you make it back home, you have the key stored back at your base, and they can recover all the data. So you don't have to be as worried about like being the chicken who pulled it too soon. If you think you're going to have a problem, if you think you're going to be falling into enemy hands, boom, delete the keys. And now if the enemy gets hold of those drives, it's nothing but gibberish. But if you make it back to base, you're good. And they can restore all that data. So it's really an awesome technology, and the ability to recover, to delete something and still have the possibility of recovering it. And then physical destruction. Physical destruction, most common method advocated here is like shredding up a hard drive or crushing it. They use these kind of like shredder devices almost. But you see people advocating for normal consumer use, just like a nail gun or something, or even literally a gun. I've seen people like, yeah, put a 45 round through it, bang, with a pistol, and that'll take care of it. You can see I don't use auto update for things because I like to be able to do it manually, and so I get these pop-ups. But so that kind of thing, and yeah, I mean, against like your regular kind of thief who's going to go into your trash or at the dump and go through and find old hard drives and try to recover your data. Sure, if they find a hard drive that's got a bullet through it, they're not going to try to recover that. But if you're a spy agency, well, that's not good enough because your data. There's enough people with enough resources to whom your data is valuable enough. They may try to reconstruct it from the parts of the different drive platters that are still fine, and you really want to shred that up. And given, like we said earlier, the increased density of data, even shredding is not a great idea because one little tiny shred of hard drive platter could have a ton of data on it. Now, of course, they're spinning platters, so the chance that you're going to have a stripe with any significant amount of data is not interrupted and broken into lots of tiny bits. So trying to put them all together in the right order and then try to reconstruct them would be extremely difficult. But the really right method for this is really thorough shredding, or even better, they actually make and this is the best thing I've ever seen, where you can literally put the thing in and it just gets melted down. And that's an amazing technology. It's expensive. Only places like the kind of spy agencies you'd think might have them do that. But that's really cool to see. It's like the end of Terminator 2. I mean, you throw it in there, it just goes. You just throw hard drives in there. It's like throwing the ring of power into the mountain in Mordor. And that's what I used to call it. I used to call it Mount Doom. Okay, data leak prevention. So DLP. This wasn't as popular of a question. This is software typically. And basically, it's whether it's implemented in some kind of hardware device or not. Really, it's software that attempts to prevent people from moving data off of your machine or off of your network that you don't want them to move off. Network DLP is typically kind of like network IDS. It's viewing traffic that goes by and attempting to identify traffic that you don't want it to allow. It could be inspecting all the emails out, or it could just be inspecting all of every byte that goes out the network. It has the same problems as most network IDS, which is that, first of all, so much network traffic these days is HTTPS, and at most organizations they allow you to use at least some limited use of personal use of your machine. So one problem is, even if you're doing HTTPS inspection, which is a thing you can do these days, if you own the network, you're able to decrypt the HTTPS traffic and view encrypted traffic. But the problem is you still don't want to do that for every category. So usually you're excluding things that are categorized as healthcare sites, personal banking sites, because you don't want to be decrypting people's personal stuff who are your employees. It may be against the law, or it may just be kind of feel like a shady thing to do, even if your lawyers have determined you're allowed to do it. So network DLP, in my opinion, is never very thorough all by itself. It's never enough. So endpoint DLP is where you've got an agent on the endpoint and it's watching. So since it's on the endpoint, it can see everything, including your banking and healthcare stuff. But hopefully it's not recording all of that and it's just sort of looking at it and then ignoring it. So I'm not sure how that's any better, but endpoint DLP. The other thing about endpoint DLP is it can control things like USB drives. Actually, I was on an assignment a couple weeks ago trying to beat the endpoint DLP at this one company to see if we could get it to write to a hard drive, or I'm sorry, write to a USB drive, and never was successful in it. There were some theoretical ways around it, but we really didn't have time to try to do that. And then hybrid is where you basically have both. You have an agent on the endpoint, but you're also inspecting network traffic. Hybrid, like in most cases, is always going to be the best of things, because with endpoint, the problem is you're always going to have some agents on the network, or some servers or other hosts on the network that don't get the endpoint DLP installed on them, and so it's not 100. It doesn't catch everything. Network DLP doesn't catch everything. It also won't necessarily catch things if your employees take their most people have laptops these days. Your laptop's at Starbucks, and then you just move things off the network that way. So hybrid is generally the best way to go for most things that have a hybrid option these days. I'm going to stop and pause here because I got to go take care of something, and we got a bunch of things here. I got to find a way to explain these in a little less time, and I'll be right back. Okay, so I want to move forward faster, but there's one thing I wanted to say about data remnants, and that was the question I kept asking people in the discussions was what makes one better than the other, and the main answer I was kind of thinking of, that I was thinking of there, was that degaussing and physical destruction obviously make the media non-reusable. So oftentimes that's just a non-starter. You may have a reason to get rid of all the old data on a machine, but you want to be able to reuse it. You don't want to buy a new drive. And so overwriting is really about the only option there. There are degaussing methods that are less complete than regular degaussing. So we might try that first, and that there are degaussers that should get rid of the majority of data remnants without actually destroying the ability of the drive to be written to, but it may not do a very good job of the one and may inadvertently do the other. So overwriting becomes your main option there, unless you've already used encryption. Because the thing about encryption is that it's more it prevents data remnants rather than getting rid of it after the fact. So that was the kind of the consideration I was after there. Okay, so this whole thing with Biba and Clark Wilson and Bell LaPadula, especially Bell LaPadula, everyone thinks of that. And honestly, outside of a CISP-oriented thing, I've never even heard these things cited. They're CISP-isms. I mean, they're real things, but they're not really referenced much in the real world, in my experience. But Bell LaPadula is the big one that gets referenced a lot, and you'll see it. I mean, if you take the CISP test and you don't have a question on Bell LaPadula, it's a miracle. So Bell LaPadula is about confidentiality, and the key concept there with confidentiality is that in all of these, basically you have layers of sensitivity: top secret, secret, confidential. For instance, that's like the U.S. government's key tiers. So the idea with Bell LaPadula is it's about confidentiality. If you have someone you have subjects and objects, right? Subjects are the actors, the people essentially, and objects are the things that they can read and write. So Bell LaPadula is about confidentiality. And Bell LaPadula says, well, you can't read up, meaning if you are a subject at the secret level, you can't read up to an object at the top secret level. I'm going backwards. If you're a subject at the secret level, you can't read an object at the top secret level, because obviously that would be a confidentiality issue, and that's pretty obvious. That's the basic fundamental thing. But then it also talks about writing, and that's the star rule, which is you can't write down. And the reason is that if you're a subject at the secret level and you write information down to the confidential level, you could inadvertently write secret information down to the confidential level. This is a practical consideration. I used to manage the classified systems at Department of Justice, and we'd have we had all kinds of multiple different systems, top secret, secret, unclassified. We didn't really have no one has confidential systems. Who classifies anything as confidential? There's not a lot out there. There's some, but not a lot of systems for confidential. But anyway, the ability to write down was always a problem, because you might have information that is unclassified on your classified system, but you have to be very careful about writing down and making sure that someone reviews it, make sure that there's nothing classified in that, and that it's very carefully taken off that system so it doesn't become polluted with any classified information before writing down. So a 100% prohibition on writing down is very difficult to go by, because someone may have composed some document on the classified system that you don't want to have to just like literally recompose on the lower level. But generally speaking, you don't want to allow unrestricted writing down from a higher system to a lower system. And then BIBA is kind of the opposite. BIBA is not about confidentiality; it's about integrity. So BIBA is about integrity and says just basically the opposite of Bell LaPadula, which is, well, you don't want to allow someone to read down, because if they read down, they could then something on that lower level less. So it's more about what's trusted, right? That lower system is less trusted, or those lower classification objects are less trusted. So if someone reads, goes from the secret system and reads something from the unclassified system, there could be malware, say, in an obvious example, some kind of bad thing down here that then gets, then because they're reading it to this higher level system, it gets impacted. So this less trusted system could end up impacting the higher trusted system because someone reads down. And the same obvious thing is true with writing up. You're getting information from a lower system that could impact a higher level system. So it's about trust and integrity. The Clark-Wilson integrity model is more based on procedural trust, that you implement procedures for how transactions or actions that modify data get taken. This is more of a data science database kind of thing. So if you're not into databases and data science, it doesn't really make that much sense. But in a database, generally there's a set of procedures you have to go through in order to update any records or add records to a database. And so making sure that those procedures ensure that once the operation to modify or add data is complete, that the whole thing is in a consistent state, is really what Clark-Wilson is more about. Okay, so ring protection. So ring protection, very simply in a nutshell, this was probably the most popular one addressed in the discussions. You've got these concentric rings. The inner ring of the operating system, like the kernel, is where the key trusted code in the operating system runs. And then you've got multiple layers for sort of system processes that are outside the kernel, and then ultimately the outer layer would be where actual like user applications run. And so basically you just got layers of different code, and the inner ones are more trusted, and so users generally can't modify the processes on these inner layers. Even the root user generally only has access out here. The kernel is even more protected, which is why the concept of like a kernel modification rootkit is such a big deal. So data hiding is really just sort of an aspect of that, which is that the data being operated on by these inner layers is hidden from the outer layers, and that the outer layers can't impact or see or modify the data that's being operated on at these inner layers. So certification and accreditation. In the instance of brevity, I'm not going to talk about components for common criteria, but common criteria is sort of an accepted definition that's used primarily within government. A lot of this stuff impacts government systems more than other systems. What common criteria is a sort of trusted third-party evaluation of specific pieces of software or hardware that evaluates this. So like if you're a government entity and you want to buy a firewall, you want to get a firewall that's common criteria certified, or that's passed a certain level of common criteria evaluation. So certification and accreditation, the two different things. Basically, certification is the technical, going through and looking at the security controls and determining that they do, in fact, basically what certification does is determine the security controls work effectively in the way that they were described. And then accreditation is where the people who are responsible, and here's a key thing, and this is super important in the security business. If you ever find yourself as a security manager, CISO, or something like that, the people signing off here are executives, and ideally they're not security people. They're executives, all the way up potentially to your CEO. In the government, a lot of times it was like a chief of staff or someone like that. Not a technical person, not a security person. It's a person who's responsible for the business or who's responsible for the organization, who can speak on behalf of the CEO, the board of directors, or whoever is responsible, and can say, okay, I'm looking at what you're saying with the certification. So the certification might say, okay, we have these protections, but these are the weaknesses in the protections, and so we do have some risk here. And it goes back to that concept of risk assessment. There's always going to be some residual risk, and accreditation is where the business leaders, the people responsible for making decisions on behalf of the organization, say, yes, I've been briefed on the certification. I understand what the strengths and weaknesses are. I understand what the remaining residual risks in security are, and I am accepting those risks on responsibility on behalf of the organization. And I sign off on that, yes, it's okay for us to go ahead and implement this system and put it into operation. In the government, this takes the form of what's often called an authority to operate, or an ATO. And you have to have an authority to operate from a designated authority who's allowed to say that, so that your department or your organization, whatever it is, says, yes, it's okay to use this system. Okay. So cloud computing, the joke that goes around is there's no such thing as a cloud. It's really just somebody else's computer. But cloud is really a little different. I didn't even like the definitions of cloud computing I found in like the CISP textbooks and study guides and things, because I don't think they're adequate. They talk about it being, it's you're using another computer out there, kind of like the joke, really out there in the connected via the internet somewhere else. But really proper cloud computing involves a level of abstraction, or at the very least, these are the machines you're using, even the ones out there in somebody else's data center, are virtualized. And really the idea of cloud computing is that they are hardware and location agnostic. That you're, like for instance with Amazon, when you have when you bring up a virtual machine in AWS, Amazon's cloud, that machine can be seamlessly relocated, and the processes running on your machine may even be running across multiple processors in multiple data centers all at the same time. So like if you've got a quad-core virtual machine, one of those computing cores may be located in one data center and one may be located in the other data center across the street. There's an abstraction that takes place there. And so that's why it's a cloud, is that the computing resources are just are broadly distributed and used, and it's not like a virtual machine that's running on a single machine and that can only ever stay there. Okay, so software as a service. This is where basically just a specific software program or application, you're subscribing to this and using it, and it runs out there in the cloud. That would be the kind of thing like Microsoft Office 365. You're getting email software, and you're getting you can use Word online and all these other things in the cloud. Platform or Google Docs is another example. Platform as a service is where you're basically being given, is sort of like what people typically do in AWS. AWS is by far the big market leader out there. They probably have over half of that business to themselves. Microsoft Azure and Google Cloud are the other two big players. Rackspace is fairly big, and that's kind of all they do. But platform as a service is where you're being given like a host, a specific machine or machines, and you're saying, okay, I'm going to set up virtual servers, and you set up your virtual servers, and those are individual platforms. And a platform can also be a database platform. So really that's kind of like software, but because it's a lower level enabler for an application, it's usually treated under platform as a service. If you're getting like Oracle database as a service, or AWS has these custom databases they run, and you use their database service. Infrastructure as a service is where you're basically given your own set of virtualization, not necessarily hardware, but virtualization platform out there as a service. So all the routing, switching, like a whole virtual network out there in the cloud. So parallelism is just about tasks running all at the same time. Bit level parallelism is usually within a single processor, right? That's what we refer to when we talk about a 16-bit versus a 32-bit versus a 64-bit processor, is how many bits it processes simultaneously at the same time. Instruction level parallelism, this is where you have multiple instructions within one task that can run at the same time. So branching as a means of speeding up computing is an example of instruction level parallelism. Task level parallelism, here we're talking about concurrent actual full tasks that are running at the same time within one computing platform. And then data parallelism is where you actually have sort of, that's more difficult to grasp. Data being treated in parallel, data being kind of synthesized, and so you're reading, writing data, and it's treated in parallel. This is often the case in like a massive multi-node, like Amazon's website, right? So Amazon's website has to, like when they update a product in their database, when I go to Amazon and you go to Amazon, we're talking to two completely different computers. And so they actually store that data. They can't store all that data in just one sort of physical database. There's way too much need to access it simultaneously. So they have to maintain that data, multiple copies of it out there, and deconflict it all at the same time and be able to access it from multiple places. And so they store multiple copies of it in multiple places, and every time it gets updated, the integrity has to be maintained, so it gets updated in multiple places more or less simultaneously, but there is some lag there. I mean, if they update the description of a product, that won't necessarily take, someone might 5 seconds later go view the website and still see the old description as it moves throughout its parallel data storage. And so that massive database that they employ is an example of data parallelism. So there's your descriptions. Hope that's helpful. I'm going to post this, and I'm also going to post a video on the week 3 content shortly here. And busy weekend, hoping to catch up on grading and all that stuff and get out ahead of that. Also, just as a note, well, actually, no, I'm going to make this note at the beginning of the next video, so I'll sign off on this one. I'll talk to y'all later.